Hi all. So today we'll know what are zero order reactions, how it is different from other reactions. So to understand, let us consider a pool of liquid, right? As you can see here, over which I place hydrogen and chlorine. This will undergo reaction to give hydrogen chloride. So I'll write the reaction here: hydrogen plus chlorine undergo reaction to give 2HCl. As the HCl forms, this HCl dissolves in water, right? So that the volume of water increases. Volume of water increases, right? So the volume of water increases, right? So thereby the volume available for the H2 and chlorine gas decreases. So the other way, volume of the water increases, the volume available for hydrogen and chlorine decreases. Let us assume here initially I have a 10 meter cube of space here that is occupied by 10 moles of hydrogen and 10 moles of chlorine. If you look at the concentration of hydrogen, right, moles per volume 10 by 10, right, which is equal to 1. Likewise, the concentration of chlorine is given by 10 by 10, which is equal to 1. As time proceeds, right, the volume available for hydrogen and chlorine decreases, right, and at the same time as the reaction proceeds, the number of moles of hydrogen and chlorine also decreases. See this, tabular column. Say at this time I have a 2 meter cube of space volume and 2 moles of hydrogen and 2 moles of chlorine. Now here we look at the concentration 2 by 2 which is equal to 1, 2 by 2 which is equal to 1. So here as you see, the concentration of hydrogen and chlorine at any time remains same, but actually it is being converted into products. So don't be confused. Right? Next, let us take the example of decomposition of ammonia over molybdenum catalyst to give nitrogen and hydrogen, right? So let us assume this is the molybdenum catalyst occupied by ammonia molecules. Occupied by ammonia molecules. So what happens? The ammonia molecules come and attach over the surface of the catalyst, and it decomposes to give N2 plus 3H2, right? So as soon as the product forms, there is a vacant space here, and that is readily occupied by the pool of NH3 molecules available over the catalyst surface. Likewise, it happens everywhere. It happens everywhere, right? But if you look uh, at any time, the concentration of ammonia molecules on the surface of the molybdenum catalyst is same. Right? We'll take one more example: decomposition of nitrous oxide. Decomposition of nitrous oxide over platinum catalyst gives N2 plus half O2. So here also let us assume this is the right platinum catalyst, and nitrous oxide comes, attached over the surface, undergoes decomposition N2 plus half O2, and the same thing happens at all the active sites of the catalyst. Right? As soon as the product forms, there is a vacant space that is readily occupied by the nitrous oxide reactant molecules, which is present over the surface of the catalyst. If you see in all these examples, right, the concentration of reactants seems to be remain same, right, but actually the reactants is converted into products as time proceeds. Okay, let us see what happens. What is the definition given in the textbooks? Reactions in which the rate of reaction is independent of the concentration of the reactants are known as zero-order reactions. So we know, let us take what is generalized rate expression. Rate is given by rate constant into concentration of reactants. The concentration of reactants, right? So we know in all these previous examples what we have discussed, the concentration remains same. So the rate of the reaction remains same because the concentration of the reactants is constant, right? So that's what theoretically definition is. But what is instantaneous rate reaction? We know minus dCA by dt equal to K into concentration of the reactants. Concentration of the reactants. We know, we have seen in the previous examples that concentration of reactants same, right, as time proceeds. Let us assume this being some constant C, right, and the multiplication of this constant C and the rate constant going to be one more constant. Let me write it as a minus dCA by dt equal to K suffix Z, right? So rate constant for the zero order reactions. If I rearrange it and integrate it, what did I get? Minus dCA equal to Kz dt. So minus dCA integrating from Ca0 to Ca and integrating from 0 to time t Kz dt. So if I put the integrate and put the integration constant, finally I arrive at the expression Ca0 minus Ca equal to Kz into T. So if I rearrange Ca equal to Ca0 minus Kz into T, which is of the form y equal to C plus mx. So what it is happening is concentration of the reactants is decreasing with respect to time with the initial concentration Ca0 and the slope of the curve is minus K suffix Z. So what actually is happening is the concentration of reactants is decreasing and the rate of decrease is as given in the figure, right? Don't assume that the concentration of the reactants remain unchanged with the in zero order reactions. The reactions undergo change, but if you look, the concentration of reactants seems to be same as we discussed in the previous examples. Now let us see half-life of a zero order reaction. What do you mean by half-life? Time required for the concentration to drop to half its value, HALF, half its value, right? If you take the previous expression, that is Ca equal to Ca0 minus Kz into T, and if I rearrange it, so T is going to be Ca0 minus Ca by Kz. So this will take the value of Ca0 by 2. Then finally we arrive at, if I substitute, T half is going to be, let me take different color, T half-life is going to be Ca0 by 2 Kz. And time of completion, time required for the concentration of the reactant to drop to zero value. So here time of completion is going to be Ca0 minus Ca by Kz. So this will take the value of 0. So the time of completion of a zero order reaction is given by Tc equal to Ca0 by K suffix Z. And what are the units of K? And we know the units of rate constant are given by time inverse concentration whole power 1 minus n. So for zero order reactions, n takes the value of 0 and the units of rate constant are going to be time inverse concentration. So this is what all about zero order reactions. I assume you guys will got to know some flavor about zero order reactions. Thank you for watching.